G'day lads and ladies, welcome to this week's episode of What's Up Mate, a podcast for electricians, air conditioning and refrigeration techs, or those aspiring to be. You're with your host Jake Sparrow. Today is Sunday the 8th of September. Between taekwondo, swimming, kids parties and a bike ride this afternoon with the kids, I found some time to record this podcast to help you get the most out of your trades. So let's chat AS3000, or as some call it, the Bible. This standard is likely going to be the first standard you'll come across in your electrical apprenticeship and even your refrigeration apprenticeship. It covers the rules around how we apply fundamental principles, arrange, control and protect circuits, select and install wiring systems with reference to AS3008, select and install accessories, install earthing systems, navigate through the damp situations, comprehend special electrical installations, test and verify our own installations as well as others. So once you've got a firm grip of this standard, your day-to-day installs will get quicker, you'll understand what's compliant and non-compliant quicker, and you'll have a great foundation to build upon your knowledge of this very rewarding industry. Also, there's a list of appendices which hold some very valuable information, including Appendix A, which references all applicable standards that reference or are referenced throughout our industry. So buckle in as I run through sections 1 to 2 in part 1 of this multi-part series. But your first little tip is actually check out the index starting on page 578. This is your cheat sheet for looking up clauses using industry-specific wording. Check it out. It's actually going to save you hours of time flicking through pages looking for clauses. Just a heads up also, the little red asterisks or stars next to text in this document actually identify amendments to the standard or a change to the previous document version, and a full list of these changes are available from page 4 of the document. You'll likely get a lot more out of these episodes if you actually have a copy of AS3000 2018 to read along with as I go through this podcast. A hard copy would be best so you can add sticky notes in preparation for your schooling, capstone or even day-to-day use. So if you have an aha moment, just bookmark it, take note of it, or write your understandings next to that clause. So first up, we're going to touch base on section 1, which is scope, application and fundamental principles. Scope. So this section actually defines the purpose of this standard, which is, in short, is actually to protect humans, livestock and property from the effect of electric shock, fire and mechanical harm from electrical installations, including machinery supplied by electric means. Application. This standard needs to be read in conjunction with other legislative requirements required in your specific state. So in South Australia, a straightforward example of this is the SA Power Network service and installation rules. Although people refer to this as the Bible, AS3000 is not actually the be-all and end-all. It's just the foundation of the ruling around the electrical industry within Australia and New Zealand, as well as being the bare minimum of installation practices. Remember, we can always go above and beyond the standards as long as we comply with the scope. So, definitions are actually also listed in section 1, starting on page 34. And they actually apply to specific wording within AS3000. So if you're unsure of exact meaning of a term, it will actually be defined in section 1. So key takings, I guess, for me, going through like how to understand this book and standard are definitions of shall. So that's clause 1.4.107. So shall indicates a statement is mandatory. So you shall do this. 1.4.108 should indicates a recommendation. So they recommend, although you don't have to do it, it's a recommendation that you probably should do it. So basically, if a statement is shall be installed with RCD protection, you must install the RCD protection and is not permitted to be omitted. So an earthing conductor shall not be switched indicates a statement that must not happen. So if a statement contains should, it is recommended. However, it can be omitted if you can justify your decision. So a good way I was taught, both in my apprenticeship and my time in the fire service, is if you can stand in front of a coroner And hand on heart, say you did all you could do to prevent injury, death or loss of property, you've done at least the minimum that was required of you in that sort of should scenario. Another example is you should subscribe to this podcast and you should tell your mates about it, along with the Instagram page. So there are pages and pages of definitions that I won't bore you with, but I recommend you in your own time go through and have a read and understand them. And if you're not sure about the definition, just ask. So ask your mentor, your trade school teacher, your tradesman at work, your mate at work. Just ask a question. It's easy as that. So section 1.5, protection against dangers and damage. So 151 states protection against dangers and damage is the requirement of this standard are intended to ensure the safety of persons, livestock and property against dangers and damage that may arise in the reasonable use of electrical installations. Again, we can't stop stupid from happening. Stupid people will do stupid things, but as long as we meet these minimum requirements, our asses are covered. So this clause runs through risks associated with the industry and how we control them. These risks are shock current, excessive temperature, so fires, degradation of wiring and other components, explosives atmospheres, so some areas are classified as explosive and very specific requirements around these, and that's a whole different certification that you need to do. And AS3000 only just sort of skims the surface on this stuff. 152, control and isolation. So electrical installation shall be provided with control and isolation devices to prevent or remove hazards associated with the electrical installation and to allow maintenance of electrical equipment. So this indicates the requirements of isolating equipment from all sources of external supply for service, maintenance and replacement of electrical equipment, including wiring. So note the difference here and the reference for needing to isolate the neutral conductor for some specific applications and how this will actually be worded. So the difference in active and live conductors is, in simple terms, active, a conductor with a voltage between that conductor and neutral and earth. A live conductor is a conductor that forms part of the electrical circuit in normal operating conditions, including the neutral conductor. So just remember, you don't actually ever isolate any part of the earthing system. So 1.4.5 actually defines active or active conductor. Any conductor that is maintained at a difference of potential from the neutral or earthed conductor in a system that does not include a neutral or earthed conductor, basically is a live conductor. Live, so energized or subject to hazardous, induced or capacitive voltages, is 1.4.78. 1.4.79 live part, a conductor or conductive part intended to be energized in normal use, including a neutral conductor and conductive parts connected to a neutral conductor. So perhaps you've got a neutralized switchboard. 1.5.3, protection against electric shock. Generally, protection shall be provided against shock current arising from contact with parts that are live in normal service or parts that become live under fault conditions. So there's actually multiple ways to satisfy this requirement, and we're going to list them now. So we've got 1542, so methods of protection. For basic operation, basic protection shall be provided by one or any combination of the following methods. So we've got insulation. So example for that would be cable sheathing. Let's just check. You can just check out 1.5.4.3 for that. B, barriers or enclosures in accordance with clause 1544, being removable by use of a tool only. That's why I guess junction boxes have screws and not just clips, and why most commercial industrial switchboards have a main switch that is required to be in the off position before opening the panel, or by bypassing the locking mechanism with a tool to only allow access by suitable personnel. We can install obstacles in accordance with clause 1545, or we can place things out of reach in accordance with clause 1546. So I guess exposed buzzways for gantry trains potentially is a really good one, being placed out of reach, or even your exposed aerial conductors out on the street. In some older areas they're all bare copper, there's no insulation on them, so that's a very good example of placing out of reach. It's actually really important to note that RCDs aren't recognised as a sole means of basic protection against contact with live parts, but may be used to augment one of the above methods. So just augment basically means to make that protection stronger. 155 covers fault protection. So protection shall be provided against dangers that may arise from contact with exposed conductive parts that may become live under fault conditions. So there's a few ways we can do this. Automatic disconnection of the supply on the occurrence of a fault likely to cause a current flow through a body in contact with exposed conductive parts, where the value of that current is equal to or greater than the shock current in accordance with clause 1553. So we then can also prevent a fault current from passing through the body in the first place by the use of class 2 equipment or equivalent insulation in accordance with clause 1554. So this is probably where you're going to start to see your double insulated fittings. Probably going to see more so double insulated light fittings than you are appliances. There's also prevention of a fault current from passing through a body by electrical separation of the system in accordance with clause 1555. So note that clause 7.4 provides further guidance on electrical separation, but this is where we can have a separate electrical, so it doesn't actually reference the earthing system. So transformers, isolation transformers, things like that. The most common form of protection we're going to find out there is actually automatic disconnection of supply, which is satisfied by the use of RCDs and correct fault loop impedance values, which need to be tested despite being RCD protected, contrary to popular belief, because basically we all know that RCDs fail. So we need to ensure that in the case that the RCD does fail, that the circuit breaker is actually going to trip within the time limit of automatic disconnection of supply. So just to protect bodies from that rise in touch voltage. Right, section 1.6 is going to touch very briefly on this one, is the design of an electrical installation. So we've got to design it to protect persons, livestock and property, obviously, from any harmful effects. We've touched on that, we don't need to run through that anymore. We need to make sure it functions as intended. Connect, operate safely and be compatible with the electricity distribution system or other sources of supply to which the electrical installation is to be connected. We also need to facilitate safe operation, inspection, testing and maintenance, as well as, this is the new one, reduce inconveniences in the event of a fault. So in the domestic market, perhaps reducing the inconvenience in the event of a fault is using RCBOs instead of a combination of circuit breakers and safety switches. If you get a fault on one circuit, you lose one circuit as opposed to potentially losing up to 3. A few design characteristics that we're going to have to look out for. Current type, is it an alternating current system, or is it a direct current system? The nature and number of conductors, so active, which is your phase, neutral and protective earthing and equivalent conductors for DC, voltage and voltage tolerances. Now, Australia is 230/400 volts for a 3-phase system, plus 10% or minus 6%, which basically gives us a phase voltage, so phase to neutral limit of lower limit of 216.2 volts up to 253 volts, and a line voltage phase to phase of 376 volt as your minimum, up to 440 volts. Now, anything out of those parameters could be an issue because of voltage rise, voltage drop, a supply authority issue, all sorts of things. So it's important if we identify that, first point of call, probably a fault loop impedance test, checking solar inverter settings on sites that you've got access to. If none of that sort of flags anything, let's escalate that pretty quickly up to your supply authority. So in South Australia, SA Power Networks. We're also going to have to look at things like frequency and frequency tolerances of the grid, but also the equipment we're installing. We've got to look at also maximum current that can be supplied. So there's some rural applications that we might only ever get a single phase swirl line to. So we're going to have to look at maybe supplementing supply. Prospective short circuit current, we're going to need to look at obtaining that information from the supply authority. So in the event of a short circuit fault, how much current are we going to expect from the supply authority's transformer? Some sites have their own on-site transformers. Again, that's going to be case-by-case basis. We've got to also look at protective measures within the supply. For example, the MEN system. We also need to limit the use of equipment sometimes. So perhaps noise from generation equipment. If we don't want to have generation equipment running where it's going to disturb, people's quality of living in their own homes. Harmonic current or other limitations. So harmonic current is caused by equipment that do not have a power factor of 1. So any inductive or capacitive loads basically has the chance of creating harmonic currents. Maximum demand of the installation is something we really have to sort of focus on. There's a few ways of doing that. Generally, my experience on this is either doing the calculation method using the appendices, or we've actually got a software that does that for us now as well. The other option is we can obviously measure it, and we can also set it. So set your maximum demand by a current limiting device. These things they're all specified in clause 2.2.2. We're going to touch on that very shortly. Utilisation voltage. Basically, the voltage supplied matches the equipment requirements. So pretty obvious on that one. We're not going to try to connect something that's like a 3-phase bit of equipment up to a 230 volt supply. It's never going to work. And even if we've got a phase converter, just be very mindful of electronics. Those phase converters are probably only really good in my experience for motors, 3-phase motors, things like that. So just be really super careful if you're ever even looking at using a phase converter or a phase changer. And we've also got to design circuit arrangement, so the number of circuits to avoid nuisance tripping, overload, match demand of the installation, and also facilitate safe operation, inspection, testing, and maintenance. So these are just a couple of those design characteristics that we really need to check out. Section 1.7 covers off on the selection and installation of electrical equipment. So electrical equipment forming part of an electrical installation shall be selected and installed to operate in a safe and reliable manner in the course of normal operating conditions. Obviously, fault conditions are out of our control. That's why we call them faults. We also need to select and install them so as not to cause a danger from electric shock, fire, high temperature or physical injury in the event of reasonably expected conditions of normal operation, overload, fault, or external influences that may apply in the electrical installation. And also, electrical equipment shall be installed in accordance with the requirements of the standard, the additional requirements as specified in the manufacturer's instructions. So, AS3000, again, minimum standard. We also need to abide by the manufacturer's instructions. In most cases, manufacturer's instructions will actually overrule AS3000. It's also really important to note that we can only install equipment that is approved for installation within Australia, and that it is suitable for our design frequency and voltage. This can be achieved easily from our end by installing products sold by trusted suppliers or wholesalers within Australia, and ensuring that any products supplied by clients have the suitable approvals. So if you're not sure, ask the client for the approval certificate. If they can't provide one, don't install that equipment. It's easy as that. I actually had one pretty recently for a new manufacturing company manufacturing edible coffee cups of all things in Lonsdale, South Australia. The machine they imported from China, believe it or not, had no approvals, readily accessible live parts, like you could stick your finger in these terminals. Non-compliant wiring, it was really brittle, straight from the factory, it was horrible stuff. We actually also had multiple mechanical crush points, and there was actually no e-stop features or machine guards on this. At the end of the day, you're not actually obliged to install equipment supplied by clients. So if they can't give you those documents to prove that it meets the standards that are required here in Australia for safety of obviously not only them but potentially their workers, but also you and your livelihood and your family's livelihood, I would recommend walking away from the job. That's what I've done in this instance. It's not up to us to do the homework for them, because guess what? You're not going to get paid to do that. Unfortunately, there's always going to be another contractor out there, or maybe some sort of a handy person out there who's going to actually install this equipment to make a quick dollar. But please don't stoop down to that level. We are working in very dangerous industries, both in the electrical and refrigeration fields. So it's important to keep safety at the top of your list. Moving on to the next one is damp situations. So 1.7.4. Obviously, water and electricity do not mix well at all, so extra care is going to be required in these situations. There's a whole section of damp areas in the book, but we're just going to cover off on this. Electrical equipment used in damp situations shall be selected and installed to operate safely near or within a damp or wet environment. Provide additional protection against electric shock in locations where the presence of water or high humidity even presents an increased risk, and also provide adequate protection against water damage that might reasonably be expected from the presence of water or high humidity. So we're going to start looking at IP ratings and things like that. How we're sealing cable penetrations, all sorts of fun stuff. So it's a very specific area, damp situations with lots of exclusion zones, things like that. We'll touch on that in a later episode. Clause 1.8, basically we're going to start looking at verification, which in layman's terms is inspection and testing. So all electrical installations and any alterations and repairs to electrical installations shall, prior to being placed in service or use, be inspected as far as practicable and tested to verify that the installation meets the requirements of this standard. So that's section 8 of the rulebook is actually a whole section on testing and verification. It actually also references certain standards that we need to look at when we're testing. So we'll touch base on that again in another episode. Precautions are going to have to be taken to avoid danger to persons and to avoid damage to property and installed equipment during inspection and testing. So just things like making sure that we've got our testers set on the right voltage. We're not putting 500 or 1,000 volts down a domestic installation with potentially connected equipment. So where the installation is an extension or alteration of an existing install, it's going to be verified, it shall be verified that the extension or alteration complies with this standard and does not impair the safety of the existing installation. So the correct connection of conductors to protective switching and control devices shall form part of this verification. Notes. Section 8 sets out requirements for the verification and testing of electrical installations. Appendix K provides a switchboard requirement summary with guidance on inspection and verification of switchboards, and we're going to deep dive into section 8 in another episode. Alterations and repairs. So section 193, alterations to electrical installations shall comply with all relevant provisions of this standard. Alterations to electrical installations shall not cause any portion of the original electrical installation or electrical equipment connected thereto to carry currents or sustain voltages in excess of those permitted by this standard, or be used in any manner that is not in accordance with this standard. Alterations to an electrical installation constructed to a Part 1 design and installation solution shall not alter the compliance of that installation with Part 1 of this standard. Note, Appendix I will provide you some guidance on the ratings of overload protective device where alterations or repairs involve the use of the existing imperial conductors. So a lot of the older homes, factories, commercial buildings in and around Australia have obviously still got this old existing imperial wiring within it. So we just need to make sure that we're complying with the current carrying capacities of these older conductors. But we also want to make sure they're still fit for use too. So 1932 covers off on repairs to existing electrical installations or parts thereof, which may be effected using methods, fixtures and fittings that were acceptable when that part of the electrical installation was originally installed, or with methods, fixtures and fittings currently available as direct replacement, provided that the method satisfies the fundamental safety principles of Part 1 of this standard, so the part that we're actually chatting about now. Note, again, Appendix I is going to provide guidance on the rating of overload protective device, blah, 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 with those conductors. So they've just doubled up on that note. It is pretty important just to check that out, just because it looks like it's slightly the same, like it is pretty close to being the same size. That current carrying capacity of those imperial conductors can differ quite a bit to the new equivalent, I suppose. And section 1 is basically, in a nutshell, just summarise section 1. It actually identifies what we need to do to protect people, livestock and property, and it references it to sections 2 to 8 on how we actually go about doing that. So section 1 is, again, just identifies what we need to do to protect people, and then sections 2 to 8, that is how we're going to go around doing it. So have a read of section 1 yourself, and we're going to move on right away to section 2. Section 2. 2.2 is basically the arrangement of the electrical installation. So circuits 2, 2, 1. This one's pretty good to wrap your head around, especially when you're doing first and second fix wiring in new construction. Circuits need to be grouped to suit any requirement for operation as a group and any special need identified by the user or equipment manufacturer to work as a group. So circuits also need to be designed so they can handle the load and operating characteristics of the equipment you're attaching to it. The limitation of consequences of circuit failure, including loss of supply to critical equipment, overload, and the ability to actually locate a fault. And the circuits must also facilitate maintenance work to be undertaken and alteration and additions to be performed without the need to interrupt supply to other parts of the installation. Right, so all conductors of a final sub-circuit or a sub-main shall be connected at one switchboard. So you can't pull neutral from one board and an active from another. Same with, you really probably want to avoid pulling a neutral from one circuit to supply another circuit, because under certain conditions you can actually overload that neutral conductor, and as we all know, we can't put any sort of overcurrent or fusing into a neutral conductor, so it's super dangerous. So we just need to make sure that if we start a supply at a specific switchboard, the actives, the neutrals, and the earthing all need to originate from the same switchboard. Common neutrals, so there is such thing as a common neutral. Back in the day, it was used quite a bit for commercial lighting, industrial lighting, where you'll run multiple phases out to your field wiring, final sub-circuits. But it's, that main neutral, you would generally just connect onto it without breaking the main neutral run. So pretty hard to do. It's just much easier nowadays just to run up multiple circuits. Each single phase and multi-phase circuit that requires a neutral conductor for the operation of connected equipment shall incorporate a neutral conductor. So again, a common neutral conductor may be used for two or more circuits originating from the same supply if the continuity of the common neutral conductor shall not depend on connection at the terminals of the electrical equipment, including control switches. Final sub-circuits that contain a common neutral shall be controlled and protected by linked circuit breakers or linked switches. So if there's a fault on one, it shuts them all off. The neutral conductor shall be marked at switchboards to identify the associated active conductors in accordance with clause 2.10.5.5 and alternative sources of supply to a single appliance such as water heater, space heater or air conditioner shall have a common isolating switch. So for example, there you got an outdoor unit and an indoor unit in the roof for a ducted air conditioner perhaps. You've got one isolating switch adjacent to the outdoor unit which will isolate the outdoor unit, but in turn also isolate the equipment within the roof space. So a basic example of, another example would be with multiple circuits, like a common neutral would be an electric storage hot water heater using a peak and off-peak element, sharing one neutral conductor. So it's important that the load is split up over two separate phases, or the neutral is sized to be able to carry the full neutral current of both loads. So for example, you may have a hot water service adjacent to the meter board with two 16 amp elements. If you share the same phase, so like let's say you've only got a single phase property, for those loads, you're going to actually need to ensure your neutral is going to carry up to 32 amps. However, if you split your loads over two phases, you need to ensure that your neutral can carry 16 amps. There's a couple of ways about protecting this. In our experience, we use the Hager 4-pole RCBOs. There's a special way to wire those up so your test button will actually function. But that way you're protecting you've got nasty protection for starts, which is a big bonus. If you've got a fault in either of the active circuits, you'll interrupt both at the same time. So it ticks all the boxes there. You can still use your test button, and it just makes it super safe as well. So moving on, we're going to touch base quickly on maximum demand. We've actually touched about this in section 1, but 2.2.2, maximum demand in consumers, mains, submains and final subcircuits, taking account of physical distribution and intended usage of the electrical equipment in the electrical installation and the manner in which the present requirements might vary, shall be determined using one of the methods set out in items A to D. So A to D, 4 different examples of how we can do this. So we're going to calculate it. So we can calculate the maximum demand using Appendix C or software, which we use Cable Pro by Elec software. Assessment, so you can use this for fluctuating loads from equipment. Occupancy rates or large complex installations. I've not ever actually used the assessment method before, to be honest. I've used calculation, measurement and limitation. So the third one is measurement. So we can use a data logger to measure the highest rate of consumption of electricity recorded over a 30-minute period when the demand is at its highest. So we've got a data logger that will measure up to, it can measure as long as you like. We generally measure a demand period of 5 seconds, but we look at the whole week's worth of data for that, and we'll break it down. We'll pinpoint exactly how much demand and how much constant demand there is at that rate, and that's how we would then measure maximum demand. So this is a really good way of measuring maximum demand if we're going to want to do an upgrade or actually have a look to see capacity for existing supplies. And then D, limitation, which in my experience a lot of people use because it's the easiest way. Especially in domestic, people go, you're going to have a single phase 63 amp supply. We're going to do that by limitation of your 63 amp meter isolator, which is your load limiting device. Again, you could just say, 2-phase 63 amps, 3-phase 63 amps. In South Australia, it's actually cheaper to get a 3-phase connection for a domestic application, as long as it's obviously run out in the street. So a lot of guys and girls out there, they're just going, hey, let's give you a 63 amp 3-phase, which pretty well future-proofs, especially with the movement towards getting everybody in Australia off natural gas or LPG. People are just going, hey, let's future-proof your place. Let's go 3-phase connection, 63 amps a phase. Bingo, bango, job done. So they're the 4 ways. So again, calculation is number 1, assessment number 2, measurement number 3, and limitation number 4. Section 223 is the selection and installation of conductors. Now, AS3000 is very vague on this because it actually referenced AS3008, which is your cable selection. Again, there's software out there for this, which is going to make your life really easy. It'll print reports and things like that. We use Cable Pro by Elec software. Brilliant bit of kit, prints reports, all sorts of stuff, but it is super important to understand sort of the methodology behind this. So I really recommend getting your head around AS3008 before using the software. Trade schools will still teach you the old method using AS3008. There's a lot of other really helpful apps out there as well. 224 is the operating characteristics of equipment. So basically, we need to select and install equipment so it can withstand voltage that it's connected to, current it will be subjected to during normal and fault conditions that the circuit protection device will subject the equipment to. So obviously under fault conditions, your circuit protection will not trip straight away. There is a trip curve the circuit protection is going to operate within. We need to make sure that the equipment we're connecting to the wiring is going to be suitable to actually withstand that potential fault current that we're going to have flowing through there. We also need to look at things such as, for equipment, such as frequency and fluctuations from the grid or alternative supplies. Obviously in Australia we run 50 hertz, it can fluctuate from that. We just need to make sure that equipment is going to withstand that fluctuation. And things like motors and things like that, they generally will if they can tolerate fluctuations very well. It's just the speed of the motor, how the motor's going to run. It depends on the frequency, so that's why we've got variable frequency drives. Power characteristics of the equipment shall be suitable for the duty demanded of the electrical equipment. The power characteristics of the cabling. So how much power or current can that cabling sustain for an extended period of time, as per the demand cycle or the duty cycle of that equipment we're connecting. And we've also got to look at things such as the effects on the operator. So operators shall not be subjected to harmful effects to themselves or other equipment during normal operation of the installed equipment. Again, we can't fix stupid. Operators can do some dumb stuff, such as forcing resets on thermal overloads, etc., etc. But we've just got to do a bare minimum. We need to make sure we select it, install it, so it's going to withstand things how they are intended to run. Section 2.3 covers off on the control of your electrical installation. So we basically want to provide devices or means to prevent or remove hazards associated with the electrical installation and for maintenance of electrically activated equipment. So we need to make sure we hit a few key points here on this one, guys, and these are going to be isolation. So can we isolate the installation for maintenance, repairs, additions, or alterations? Can we shut it down quickly and safely in case of an emergency? And do we actually have functional control of the system we're installing? So they're the three key points that we really need to look at when we're looking at 2.3. Also, we need to make sure that we can lock out and tag out any isolation points and short circuiting. We need to be able to lock out and tag out any isolation points. So that's why we've got isolators with lockable points, so we can put a lockout padlock on there with the tag. You'll probably see, especially linesmen, will generally they'll short circuit their or earth out their equipment they're working on, as well as locking out and tagging out because of the way things are switched out on the streets. But that's only a supplementary measure. They'll still do their lockout, tag out measures. So if somebody does bypass that lockout, tag out, or they switch in another set of lines, it'll actually short out without causing personnel injury. It'll obviously damage equipment potentially, but we're really key focus here with the electrical industry, or I guess any industry really, is we're going to protect life first, then property and livestock, etc. So 23212 looks at alternating current systems. So provision of isolation of conductors in alternating current systems are as follows. So active conductors. So all active conductors of an alternating current circuit shall be capable of being isolated by a device for isolation. So again, remember, active does not include your neutral conductor. So neutral conductors, no switch or circuit breaker shall ever be inserted in the neutral conductor of a consumer's mains, or where the neutral conductor is used as a combined protective earthing and neutral conductor for protective earthing of any portion of an electrical installation. So because in Australia we use the MEN system, it's not a good idea to switch a neutral ever. So that's why we generally have, when you've got to install your generation changeover switches, when we're hooking up generators, we never switch the supply neutral. So a switch or circuit breaker may operate in the neutral conductor of circuits other than those in the before mentioned items, where the neutral pole of a multi-pole switch or circuit breaker is actually linked to the switched actives and neutrals. So we want the active and the neutral to be disconnected from that supply simultaneously. So we turn off the circuit breaker or the isolation device. In the case of a three-phase bit of equipment, the three active phases and the neutral phase will switch simultaneously, which means at the same time. For a single-phase piece of equipment, we'll have a two-pole isolation device. Again, active and neutral will switch simultaneously. Again, really important to note that we should never see a fuse installed in any neutral conductor, because it's super dangerous if we do that. It's actually pretty funny. I had a bit of a discussion, or I guess, a heated discussion with another contractor, stating that switching the neutral isn't required and it's actually dangerous. And I understand they've probably got some valid points, but if as technicians we're proving things for dead, it's not actually dangerous. So his example was 2-pole isolator switching active and neutral for an AC system. Now, we do this all the time because it's, in our opinion, switching active and neutral at the same time provides much safer isolation for technicians. Their argument was, what happens if the neutral switches off but the active is fused closed? Now, I guess their argument might be valid in the fact that, I guess, if a technician's been lazy and they don't test for dead correctly, the equipment's stopped running because there's no neutral present. So, the technician's probably going to assume, it's switched off the active. Dangerous, I guess, but if we're testing for dead correctly, and the way you're going to get short at trade school and the way your tradesman's going to hopefully teach you guys and girls out there how to test for dead, this should never be an issue. We like to install isolation devices for our equipment that we install. We like to switch all live conductors, so actives and neutrals, because when fault finding, especially using an insulation tester, you can isolate the equipment fully from the MEN system quickly and safely, and there's no more false readings down to earth on that neutral, or even your actives, especially if you've got motors or electronics. Funny, talking about switching neutrals, sometimes it's actually a requirement for some appliances, especially like things like gas cooking appliances or heating appliances. A lot of contractors do this by providing a plug and socket, so gas service techs can actually unplug the equipment fully. Others use double pole or multi-pole isolation switches or isolators for this purpose. We use both methods depending on accessibility generally, and also the requirements for isolation of the equipment, usually mentioned in the installation manual or the gas regulations. AS3000 doesn't really specify how to isolate gas appliances because we don't touch base on gas stuff. I guess for a quick example, gas cooktop power point can't be behind the oven and must be in a cupboard adjacent to the cooktop, so you can actually get in there and unplug it without having to remove other appliances. Or it must have an isolator switching active and neutral conductors somewhere accessible, and it also needs to be labelled. So all devices used for isolation shall be clearly identified to indicate the circuit or equipment that they isolate. So this can be achieved by marking, or in the case of isolation of a single item of equipment, location of the device marked on the equipment itself. Main switches. So main switches are required to provide efficient and effective isolation of electricity supply from the electrical installation or part thereof by persons including emergency services workers in the event of an emergency arising that requires prompt isolation, as well as maintenance of supply to safety services during an emergency that may require or result in isolation of supply from other portions of the electrical installation. So the supply to every electrical installation shall be controlled on the main switchboard by a main switch or switches that control the whole of the electrical installation. However, if multiple suppliers are provided, each supplier shall be controlled by a main switch or switches on the main switchboard for each supply. However, there is an exception to this ruling, especially around renewables. So alternative or supplementary supplies may be located at any switchboard within the installation, provided they're installed in accordance with applicable standards, for example, AS NZS 3010 or AS NZS 4777.1. So each part of an electrical installation supplying a safety service in accordance with Clause 7.2 shall be controlled by a main switch or switches separate from those used to control the remainder of the installation, as required by Clause 7.2.3. I guess an example for this would be smoke control fans or smoke spill fans, where the fire service are actually going to use smoke control and smoke spill fans, or even positive pressure fans to actually help evacuate a building and contain smoke damage to certain portions of the building, but they also still want to isolate all other aspects of the electrical supply that's not aiding them in the firefighting capabilities, I suppose. Other things to consider. The number of main switches shall be kept to a minimum. So why? Well, we want to keep it practical to provide for effective isolation in an emergency. For domestic electrical installations, specifically, each separately metered supply shall have a main switch, or if there is more than one separately controlled supply from a meter, a main switch for each separately controlled supply. So think a single phase meter with a controlled load output. So we've actually got two outputs on that meter. So we've got controlled load, which is controlled by the energy regulators, and then you've got your fixed supply, which is live all the time. So we need to have a main switch for your off-peak and your controlled load, and your peak, so your one that's live all the time. They need to be readily accessible, main switches, and no more than 2 meters above the ground or a suitable platform. There's a few exceptions. They don't need to be readily accessible if they are on public land. Obviously, we don't want randoms walking past and turning your main switches off for things like bus stops, traffic controls. You can just imagine the chaos of that sort of stuff. Electrical installs with more than one occupier shall have main switches that isolate each occupier's portion of the installations, but do not need to isolate the submains. So the main switch can actually be within that tenancy's subboard potentially, which might be inside that occupant's dwelling, perhaps. So it's main switches is quite a broad subject, I guess. Section 2.4. Now we're actually moving on to something probably a little bit more exciting than main switches. So it's going to be fault protection. So the following methods of fault protection are recognised in this standard. So we've got automatic disconnection of supply, the use of class 2 equipment, and your electrical separation. So the easiest way to do this, and probably the most common we're going to see out there, is going to be, especially in the domestic field, will be the automatic disconnection of supply. Protection by automatic disconnection of supply is basically just a solution that limits the prospective touch voltage arising when live components touch conductive parts or protective earthing conductors. So a way to combat this is obviously correct earthing as per section 5 and disconnection of supply by an overcurrent protective device or circuit breaker or RCD, RCBA. Equipment we can use to actually meet this requirement are your enclosed fuse links, like your offset HRCs, like the old federal fuse holders, miniature overcurrent circuit breakers, molded case circuit breakers, fixed setting RCDs. We're not actually allowed to use semi-enclosed rewirable fuses at all to satisfy this. So if we ever come across a circuit that's protected by a semi-enclosed rewirable fuse, or some people call them a surf fuse, you're not actually allowed to extend it. You're allowed to repair, but you're not allowed to extend. 2.5, protection against overcurrent. So active conductors shall be protected by one or more devices that automatically disconnect the supply in the event of overcurrent before it reaches a level and or a duration that can cause injury to persons, livestock or damage. Again, we're going back to the scope, so section 1 on that, due to excessive temperature or electromechanical stresses on the installation. So high currents produce high electromagnetic forces which can actually stress cables, etc. Overload versus short circuit, what's the difference? So overload, for example, is a motor starting and stalling. So if it's got too much load on the motor and running at locked rotor current, so that is an overload. It might not even be that fast. It could just be a slightly overloaded motor that is creating higher current flow than normal. That's an overload scenario. So in the case of this, using a MCCB, the overload action is the bimetallic strip heating over time and tripping the breaker. So depending on the extent of the overload, will depend on how fast it's going to trip. A short circuit, let's say for an example, is the motor winding shorting to an earth component or another phase or even a neutral winding in that motor. So in the case of that, the MCCB, the short circuit action is actually going to be the magnetic coil instantly tripping the breaker. So they're the two differences between overload and short circuit. Some people get them confused. hopefully that's cleared that up a bit. So overload is like over a longer period of time, whereas your short circuit will be nice and fast. 2512 covers off on consumers' mains and overcurrent protection of consumers' mains. Basically, it's going to be arranged in accordance with one of the following scenarios. So short circuit protection and overload protection shall be provided at the origin of the consumer's mains. Service fees, let's think of it like that. Short circuit protection shall be provided at the origin of the consumer's mains, and overload protection shall be provided at the main switchboard. So short circuit might be with an 80 amp service protection device, whereas the overload will be calculated to generally 63 amps in that case to protect against overload. So short circuit is upstream and your overload protection is downstream in that case. Short circuit protection for number 3 need not be provided where overload protection is provided at the main switchboard and the consumer's mains have actually been installed as per clause 39712. That's a mouthful. This is regarded as an unprotected consumer's mains, and typically this is when you're going to see that neutralisation of the switchboard, not earthing it. Obviously we can still earth it, but then we're going to have to start looking at the size of our MEN link. In my opinion, it's just easier to neutralise. So 2513 covers off on submains and final subcircuits. So general arrangement around that. Overcurrent protective device or devices ensuring protection against overload current and short circuit current shall be placed at the origin of every circuit and at each point where a reduction occurs in the current carrying capacity of the conductors. So you can actually omit overcurrent protection if the interruption of supply creates a danger greater than that of overcurrent. So for example, industrial example potentially here, lifting magnets or exciter circuits for machines. So in the event they're using a lifting magnet, so it's a big electromagnet which is controlled by electricity, it's lifting something heavy. In the event that there's an overload in that circuit, the magnet loses all its holding force and it lets go of its load, and that might crush person, equipment, etc. So we can actually omit the overcurrent protection there, but it's going to be highly recommend that we actually install an overload alarm that a user has to actually acknowledge that overload scenario is happening. Protection against the overload current. It's really, which is 253. It's important to set up your load cabling and protective devices in a way that meets the following requirements. So listen up carefully. I'm going to repeat this one a couple of times and give you a few different examples. So the load is less than or equal to the nominal current of the protective device, which is less than or equal to the continual current carrying capacity of the conductor supplying that equipment. So, for example, a compliant coordination is going to be a load of 16 amps protected by a circuit breaker rated at 20 amps, protecting a cable that is rated at 20 amps or above. An example of a non-compliant coordination would be a load of 20 amps protected by a circuit breaker rated at 20 amps, but protecting a cable that is rated at 16 amps. So we can overload that cable. In simple terms, the cable needs to have higher current carrying capacity than the load and the protection device. The protection device needs to have a higher current carrying capacity than the load, and the load needs to be less than the current carrying, the current of the load needs to be less than that of the cable and the protection device for it to actually work correctly. Some people struggle with that, but have a bit of a play with that and just look at what you see in the field. So maybe a hot water service 16 amp element, 16 amp circuit protection on 2.5, which is good for up to about 17 amps depending on length. So we smash that in there, we don't smash it, but we scrape it in there. That's just one example. So just have a look, even your light circuit, general power circuit, etc. Basically, we want to have overload protection installed at the origin of every circuit and each point where the reduction occurs in the current carrying capacity of the conductors. There's some exceptions to this when the conductor has no branch circuits or socket outlets connected between the origin of the conductor and the overload protective device, or the conductor supplies one or more circuits that are individually protected against overload, such as within the switchboard or busway, and the sum of the current ratings of the circuit protective devices supplied by the conductor does not exceed the current carrying capacity of the conductor. So let's say we've got a 500 amp bus bar supplying 4 100 amp circuit breakers. We comply there. Protection against short circuit current. Again, short circuits that real fast. We want that to disconnect really quick because that's when we're going to have high fault currents. We need to just be aware that when we're referencing AS3000 for this, that the requirements of this actual clause, so clause 254, only take into account cases of short circuit and short circuits happening between conductors belonging to the same circuit. So it doesn't necessarily take into account like short circuiting between different conductors of other circuits. Sometimes prospective short circuit currents, so that's the potential for a high fault current to be there, will depend a lot on your fault loop impedance. In some instances you may require breakdown fuses with a higher rated KA rating upstream of your submains or sub-circuit protection. So you'll typically see this in large commercial and industrial sites. So for example, you may have a prospective fault current of 7,500 amps, so 7.5 KA, and an engineer may have specified upstream HRC fuses of 10,000 amps, so 10 KA. So you can install 6 KA rated circuit protection, which is pretty common, and it's cheaper than the 10 KA stuff within all your switchboards. So in the instance of let's say in the instance of a short circuit with a high prospective fault current, the HRC fuses will actually rupture if the downstream circuit protection weld close under fault conditions. So that's what the KA rating means, is it's telling us that a 6 KA rated RCBO will withstand a fault of 6,000 amps flowing through it before it will weld itself shut and just become part of that circuit. Basically, it's become a cable. It's a conductor now. So we just need to make sure that if we do have like high prospective fault currents on specific sites, that we either upgrade all of our circuit protection. So let's say for this example was 7,500 amps, so 7.5 KA, we've got all either 10 KA circuit protection, which will add up very quickly if you're quoting that job, or we put some HRC fuses upstream rated at 10,000 amps, and then we can put all 6 KA rated circuit protection in. This section is quite large, so I'm not going to go into all of it because we're going to run over time pretty quickly. There's also multiple diagrams which are really hard to explain verbally, so I would definitely recommend having a bit of a deep dive into this 2.54 and also section 1 and all of section 2. So if you've had a look at it and things aren't quite making sense, reach out to me or your trade school teachers, wherever, and one of us will be able to help you. We also really quickly need to look at the reliability of supply. So this covers both discrimination, which is your selection, and your backup, which is what we call cascading protection. For example, if we have a fault on an appliance, we do not want the service fuses to open circuit as well as the final sub-circuit protection. However, if the final sub-circuit protection fails, we still require the service fuse to be able to operate within a set time. Again, have a read at section 2.5. It'll give you some examples and how to actually calculate that. If you're not sure, reach out. I can run you through that. So this next one's going to be pretty big, guys and girls. Section 2.6, additional protection by residual current devices. So, additional protection by residual current devices. Now, this is a pretty big section, so maybe hit pause, grab a coffee, grab some water, have a bite to eat, and then we can get stuck into it. So, the use of fixed setting RCDs with a rated operating residual current not exceeding 30 milliamps is actually recognised as providing additional protection in areas where excessive earth leakage current in the event of failure of other measures of protection or carelessness even by users could present a significant risk of electric shock. Now, the use of RCD again is intended only to augment the other measures of basic protection, so we're just sort of having that as a backup. So we still need to make sure our fault loops will pass, we still need to make sure that we've got our correct circuit protection in place. RCDs are designed to protect human life, not cabling as well, so that's really important to remember. So they're not going to pick up on a fault between live conductors, so between active and neutral, or active, so line 1 and line 2, also phase-to-phase faults. They also don't provide protection against voltages imported into the electrical installation earthing system through the supply system neutral conductor. So in the event of a high impedance neutral, we'll get a rise in the voltage. So these things, although people call them safety switches, which I don't like, because people think, oh, I've got a safety switch, so I'm safe. Well, yes, you're safer, you're not safe. We just need to make sure that when we are selling these, we actually call them residual current devices and not safety switches, because there's still risks associated to electric shock, because safety switches fail, they don't pick up on certain faults. So yeah, again, basically how they work is they measure current on your active and current on your neutral. They go through a coil, and there's some electronics in there that measure that imbalance. So as soon as the imbalance for a 30 milliamp RCD, as soon as it approaches being in balance of over 30 milliamps, the RCD will trip, and that's because it thinks that the current is leaking to earth. So whether it's that through a person or through an earth bit of equipment, it just shuts it down and things are safe. So it's a big section again. The requirements in these rules are for RCDs with a maximum sensitivity of 30 milliamps, so we can actually use 10 milliamps or 30 milliamps. RCDs with a sensitivity of 30 milliamps are actually designed to operate before fibrillation of the heart occurs, so that's where your heart will change its rhythm. And RCDs with a sensitivity of 10 milliamps are actually designed to operate before muscular contraction, so they're even more sensitive, or inability to let go occurs. So muscular contractions can result in the inability to breathe, and infants may be more prone to this risk. So there's actually a section around this where the childcare centres, medical centres, education facilities, home care, specific installs will require 10 milliamps. So selection and arrangement is 262. There's a big bit of confusion around how we size an RCD. So RCDs, like common RCDs, are sized generally with 40 amp or 63 amp. People do just go, oh, well, I've got 220 amp power circuits on a 40 amp RCD, that's all I can put on there. Not necessarily. You actually do it by the maximum demand of the portion of the electrical installation being protected by the device. So, or the highest current rating of any overload protective device on the portion of the electrical installation being protected. No earthing or protective bonding conductor shall pass through the magnetic circuit of an RCD. And RCD shall be so selected and the electrical circuit so subdivided that any earth leakage current that may be expected to occur during normal operations of the connected load or loads will be unlikely to cause unnecessary tripping of the device. So 26222, which is referencing Australia only here, RCDs can have any number of poles but shall interrupt all active and neutral conductors in the following applications. So RCD uses leakage protection devices in medical treatment areas. RCDs incorporate into a socket outlet for alterations complying with clause 26325A. RCDs located beside a socket outlet, specifically intended for the protection of that socket outlet only for alterations, again complying with clause 26325A. And RCD shall be of the type for which tripping is insured for a residual sinusoidal alternating current. Arrangement. So, where additional protection of final subcircuits is required in domestic, that's all the time in Australia, unless it's a submain or a generation supply, like solar, we need to make sure the number of RCDs installed exceeds 1, and more than one lighting circuit is installed. Lighting circuits shall be distributed between the RCDs. So in the event of a fault, you don't lose all your lights. Is basically the intent of that one. And I believe it's because somebody in Queensland, I think, got sued because a client of theirs fell down some stairs because there was a fault and they lost all their lights. I'm not sure around the exact origin or how true that story is, but that's what we were told at trade school many moons ago. In residential installations, not more than 3 final subcircuits shall be protected by any one RCD. Again, that's just to prevent loss of the whole home. And where there is more than one final subcircuit, a minimum of 2 RCDs shall be installed. So, yeah. So if you've got one power circuit, one light circuit, it's going to be cheaper for you guys just to install RCBOs. Over 2 separate RCDs, it obviously takes up less pole space. Again, these arrangements are all intended to minimise the impact of the operation of a single RCD. So, domestic and residential installations. So there's a difference between domestic and residential. Residential is generally that one living unit, whereas domestic is covering multiple living units, but also including the residential install. So it's a little bit confusing, but there we go. There it is. Additional protection by RCDs with a maximum rated residual current of 30 milliamps shall be provided for all final subcircuits in domestic and residential electrical installations where protection of final subcircuits is required. RCD shall be installed at the switchboard at which the final subcircuit originates, so we can't put one downstream. These installations include, but are not limited to, individual domestic electrical installations, residential areas of electrical installations, so pubs, hotels, multiple residential electrical installations that are provided for common use, or external lighting installations in common areas of multiple residential electrical installations. So if we go strata section, we might have a nice barbecue area outside. That's classed as multiple residential, and it's the common area. So maybe a laundry in a hotel where patrons can access. That's a common area within a multiple residential install. There's a couple of exceptions. RCD protection may not need to apply to repairs undertaken in accordance with clause 26326. Non-domestic, so 26323, and so non-domestic and non-residential installations in Australia only are not limited to these examples, but individual commercial or industrial electrical installs, multiple commercial or industrial electrical installations that are provided for common use, external lighting installations in common areas of multiple commercial or industrial electrical installations, or commercial or industrial portions of mixed installations. So the location of RCD protection where protection of final subcircuits is required, RCDs shall be installed at the switchboard at which the final subcircuit originates. Again, there's an exception where the wiring system has been installed with additional mechanical protection as required by clause 394. The RCD protection specifically intended for the protection of that socket outlet can be installed at or adjacent to the socket outlet. So, for example, that one, factory wiring where you've got your 3-phase socket with your 3-phase RCD right next to it, or even in the same enclosure. Pretty easy. So they do single-phase options for that as well. 26323 goes through the requirements for additional protection. So when do we need additional protection? And here it is. Additional protection by RCDs with a maximum rated residual current, again of 30 milliamps, shall be provided for final subcircuits with a rating not exceeding 32 amps, applying socket outlets, lighting direct connected handheld electrical equipment, e.g. directly connected tools, and direct connected electrical equipment that represents an increased risk of electric shock. So factors may represent an increased risk of electric shock include, but are not limited to, external influences. So things we can't control, weather, fauna, all that stuff. Type of electrical installation and processes being conducted. So, for example, workshop and particular industrial activities. For all other final sub-circuits with a rating not exceeding 32 amps for direct connected equipment, additional protection by RCDs with a maximum rated residual current of 30 milliamps should be considered. Again, do you want to be sitting at home one night and getting a phone call that somebody has passed away or has been injured by one of your installs because you wanted to save yourself some money on not using an RCD? I know I wouldn't, so really have a bit of a think about that one. Again, there's exceptions to these rulings, especially surrounding repairs, but it's always a good idea to install an RCD. So repairs for Australia only is covered by 26326. The requirements of this clause 263 need not apply where a socket, outlet, luminaire or single item of electrical equipment that is not RCD protected is replaced with an equivalent item in the same location. So for the purpose of this clause, the replacement of a single socket outlet with a multiple socket outlet assembly actually is deemed to be a repair, not an extension of the circuit. For medical, education, childcare and home care scenarios, which I've touched on briefly, an RCD with a rating of 10 milliamps will be required. For these installations, I really recommend engaging a consultant because there's so many rules around these things. You don't want to get it wrong, especially when there's vulnerable people like medical issues, small children that will be more susceptible in the case of an electrical shock to be severely injured, become disabled, or even pass away through an electric shock. So we just want to make sure we get that right. And if you get a consultant to do it, they've got insurance that's going to protect them and you in the case of, that horrible thing happening. So there's actually touches base here as well on arc fault protection, which may be used to prevent fire hazards in the event of an arcing fault, so like a loose connection. However, these are not yet mandatory. I'm unsure if there is even a testing method to prove. Sorry about that, everybody. That was my little daughter, Zali. She's 5, letting herself into the shed and chatting to my dog, Jax. But yeah, sorry about that. So back to where I was. Arc fault protection may be used to prevent fire hazards in the event of an arcing fault. However, these are not yet mandatory. I reckon they will be soon. I'm actually unsure if there's even a testing method to prove their operation apart from hitting the test button on them. Like with the RCDs, I like to actually use our fluke testers to test them to prove that they're working the trip current and how long they take to trip. I have not come across a tester that's going to actually test these arc fault protection devices correctly. But we've actually installed a few of these, and that was more for a peace of mind thing for our client. They had some issues with some lights coming on and off and losing power upstairs in their home. I couldn't for the life of me. I spent hours over multiple visits trying to find this fault. Couldn't find it. There was a potential that there may have been a renovation. It looked like the upper story was actually added on, and I couldn't access the wiring in between the top floor and the ground floor because it was all within that void space, and I wasn't sure if maybe the building's moved and it's crushed some cables. All my tests, insulation resistance were sweet, fault loops are all sweet. We put the logger on it. I couldn't supply always seemed to be pretty stable. So just for a bit of peace of mind, more than anything, we actually put some arc fault detection devices across all the circuits on that home. And they've not had them trip, but they've also not had the problem reoccur. So Yeah, I really don't have an answer for that one, but that might be an example of when you want to use it where you think you may have faults, arc faults. Pretty long one, guys. It's like 74 minutes. I think I've been blabbing about section 1 and 2. It was very brief. Like, it's a very big book that we need to get our heads around. I've tried to pick out the more important items from these sections for this week's podcast. However, I really strongly recommend you guys having a thorough read through the sections 1 and 2. Maybe re-listen to this podcast a couple of times with AS 3000 2018 sitting in front of you. Pay attention at trade school and ask your mentors any questions you may have. If you've got some questions about what I've covered in this podcast or previous podcasts, or you've got some ideas for future podcasts, I'd love to hear them. So reach out to me either through our Instagram, which is the What's Up Mate podcast page. I will probably get an email address that I'll share so you guys can reach out with ideas or even feedback. I would love some feedback on these. Thanks for listening, everyone. Please like and subscribe to the podcast so we can actually continue to grow the podcast to get more reach. We're hoping we're actually helping you guys and girls out in the field. So this has been another episode of What's Up, Mate? A podcast by an Aussie technician for Aussie technicians. Have a great week out there, guys, and I'll speak to you all next week. Bye.